Actually, as usual, I'm here to commence this today's proceedings. And I'm Kamala Gunwadana, council member, and I'm sharing this knowledge sharing sessions this year from the Civil Engineering Sectional Committee. So, as you all know, our resource person today, Professor Tishanjay Singh, again, Senior Professor of Civil Engineering at the University of Moratuwa, who doesn't need any introduction now. So, the title of the today's lecture of our veteran professor, Tishanjay Singh, is Modeling of Inverted T-type Foundations for Multi-Story Buildings for Low-Rise Buildings up to about 5 floors. How these inverted type T-type foundations can be used successfully to provide a good foundation. So he will describe the computer modeling of inverted T-type foundations in detail with examples. So my final remark here is we are much fortunate to share more fruitful lectures, programs from Professor Jayasinghe, his expertise areas during this session as the chairman of Civil Engineering Sectional Committee. So please enjoy this important lecture, and without further ado, I invite Professor Jayasinghe to commence your lecture. Thank you. Over to you, Professor.
Thank you, Engineer Kamala.
Welcome.
Right. Thank you. I'm get this sorted out. First, let's talk about the different types of soils we can encounter and where we will be using inverted T-types. Inverted T-types. So basically, if you have a structure like this, let's say these are 7.5.
So can you spotlight your sketch? It's not.
You can't see it?
Can see, but it's in the small version. You have to spotlight.
No, it's in the large version. How would that be? On my computer, it's on the large version. On yours, it's on the small version. Well, let's see.
Okay. Yeah, Professor, done.
It's done. Okay, just one moment. Now is it clear?
Yes.
Yeah. Okay. Sorry about that.
Thank you.
So basically, you get and then let's say we have some shear walls. There are 2 lifts, and to balance that, we have done something like that. And in these areas, you get washrooms and other facilities. And now, if you are designing a building like this, and let's say when you look at from the side, you get floors. There are about 5 floors. So you get a structure like this. Now, so initially we put all that on supports because we cannot design the foundation at the beginning. So we consider that we are going to have a good foundation. So the first thing is how are we going to model this? How are we going to design a beam on this structure? how are we going to design a beam on this structure? And so it's a low-rise building. And let's say we have this assumption. All vertical loads by the frame because, number 2, there are strong elements to provide lateral stability. So all the vertical loads are resisted by the frame because all there are strong elements to provide lateral stability. So if you look at this direction, X direction, here we have a wall, and here we have walls. So we can resist it. In the Y direction, also you get like that. So you can say, you don't have to worry. This is a low-rise building. The lateral loads can be resisted by the vertical, by the frames, by the walls, and the vertical loads can be carried by the frame. And there's no there isn't much interaction because the walls will behave like this, and it dominates. Up to about 10 stories, this behavior dominates. Beyond 10 only, the behavior of the shear wall becomes a little less prominent. And in such situations, we have to go for wall frame interaction. So here, you don't need any sophisticated modeling. And so what we can do is, we can design a beam. How to design a beam? What we do is, we'll have to make a model of the structure. And how do we make a model of the structure? We say, we are going to have the beam and the columns. And then we are going to say, I'm going to fix it here at the remote ends. But here we have to be very careful when we are doing the modeling because we have to put this on rollers. So it does not move any direction, but it can move vertically. Unless you do this, you'll get wrong answers because if you don't have rollers here moving vertically, it's like a structure suspended from above. In our structure, the structure is not suspended from above. Nothing to resist it. So it all shortens this way, downwards. So we have to get a model like this. On this model, we can say maximum load, minimum load, maximum load, minimum load. And we can say all maximum, and then minimum, maximum, minimum, maximum. So we can get the envelope. And when we get the envelope, we have to think about moment redistribution. You have to think about moment redistribution, and so moment redistribution, and that is, we get bending moment diagram like this due to this number 1. And we get something like this due to number 2. And this is number 3. And this is number 3. We get something like this. Something like this, number 3. And this is number 1. And this is number 2. Then what we do is, you can clearly see that we can do some reduction in the support moment. And you can easily do up to 10% moment reduction. 10%. And if you go up to 20%, then you have to be careful when you're calculating the steel. But if you do up to 10% moment redistribution, the design is exactly the same as a normal design, but you can make a saving in the amount of steel needed. So this way, you can easily design a beam because the bending moments are known. And when the bending moments are known, finding the reinforcement is not a major problem. You can always find it, and then you can detail it in a logical manner. So if you have any doubt, please refer the book by Mosley and Bungie. And once you have enough knowledge, refer the book by McGinley. So both for Euro, and they are all both very good books. But don't read this first. You read this first, it will be disaster. So read this as first book and this as second. So when you have a good knowledge of Euro code, you can read book number 2, which will give you an insight into more advanced design techniques. So basically, designing a beam is not a big major problem. Then, when you do the design, we can create a frame, to select one frame, and we can create a frame like this. Our frame. Now decide whether to go for this or whether to go for this. So we have a question. A or B. So we have to look at the soil condition. Laterite. Sandy. Or you can say clay sand. Clay sand. Sandy clay. So we have 4 types. A, B, C, D. Now what is A? Earlier Europe was like this, Africa was big. So India broke away, Australia broke away, Australia went this way, India went, turned and hit the Europe, and it created Himalayan mountains. In this journey, both these countries went through a burning patch, and that converted all metamorphic rock to solid rock, because the rock was heated up, and that created a very special rock. And so we have bedrock very close by, and we have bedrock very close by. So what happened was, when you have bedrock, we get hot or warm rock, and you can have thin soil
Okay.
cover, it's also warm. And what happens is
ඔයා රිවිව් එකක් කරන ප්‍රේසි නම් කියන්න. ආව බලාගෙන යන්න නෙමෙයි නිකන්.
what happens is during when it rains,
sorry.
we get warm water going through the rock, and rock with undergo weathering, and it will form silt, it will form clay, and then it will form sand particles, and it will form gravel particles. And then we say, if it is in very visible sand form, we say it's fully weathered rock. But if it is available in the clay form, we call it laterite soil or kabuk soil. So if you have kabuk soil, we also have to see what are the other countries you can have kabuk soil. And 120,000 years to 12,000 years, we had the Ice Age. And the sea level was 125 meters below. So all this was one country bigger. So people could easily travel this way. And then what happened was 12,000 to 8,000 years, this melted, and at the end of 8,000 years, the current map appeared. The world map that you see today appeared only 8,000 years ago. So during that time, people tried to keep this link, so they created a bridge. And that is the bridge, part of the remaining parts of the bridge can be seen when you fly in a plane over this place. So you get a current map. So basically you can see even in Sri Lanka, the origin of the people will be South Indian initially. And then they separated, then they developed their own technology. From 8,000 to onwards, they developed their technology on their own, but they were influenced. And then about 2,500 years ago, the North Indians also came in large numbers. So we got mixed people with fair skin. So these people knew many things, and one is how to make steel, and they exported to Damascus, and it's called Damascus steel because we knew how to use steel, we knew how to use rock and soil. From the soil we made bricks, and also we made laterite blocks. And these laterite blocks are called kabuk blocks. And that is the hard laterite. And then we also had rock, and we made things like pillars. And we did not use rock as beams, but we used timber as beams. So we were able to construct buildings up to 7 floors. And sometimes it could even go up to 9 floors. And this is the palace of King Parakram Bahu with bricks. And this is Lower Mahapaya with timber on rock pillars. So if you look at all this history, if you have laterite soil, it's a strong soil, and if the water table is low, you have laterite soils, generally you can easily get a bearing capacity of 175 to 200 kilonewtons per meter square. Now, when I say the bearing capacity is this much, the bearing capacity is this much. What is the meaning of that? That's always know the meaning. Meaning is, if you apply a load of 200 kilonewtons over 1 square meter area, then the soil will settle by 25 millimeters of elastic settlement. So that is a short-term deformation. It's a short-term deformation. But in long term, there's a possibility for consolidation. But because laterite soils contain a lot of gravel, sand, something like 60 to 75%, or it can go even up to 85%. So sand and gravel content is very high. Because of that, this consolidation is not a problem. Consolidation is not a problem at all. So, because we have a strong foundation material, we can easily go for pad formations. We can easily go for pad foundations, or we can also go for combined footings. And there are YouTube videos showing how to design combined footings and isolated footings. If you just type MTR Jaisingha on internet, or not in internet, YouTube, you can watch these videos. And if you have any difficulty in watching them, you can contact Mr. Engineer Imanta at 0766872085. Please contact Engineer Imanta at this number. He's the person who is managing all these web uploadings for me. He's a fresh graduate of Boroto University who is now working at Water Board, and he's the one who actually handles all these web uploadings. And if you have any difficulty in watching any of these, please contact Engineer Mantha, and he'll be able to help you to help you, or he'll be able to send web links so that you can go to you can automatically upload the YouTubes. So if you want to know how to design a pad footing or a combined footing or strap footing, so please go to internet and see whether you can find the particular videos. And if you can't find it, please contact Mr. Imantha Dharmasiri at this particular address. Contact Imantha Dharmasiri at this particular telephone number. But please give a try to find it on the internet. If you can't find it only, please give a call, and especially during the night time, don't call him during the daytime because he's working at waterboard, doing some very important modeling for waterboard. So please don't disturb him during daytime, and in the evenings, it's okay. You can contact him and get some information. So that is the first soil condition. We said we can have laterite soil, and we can also have sandy soil. So when you have sandy soil, again, we should know the special characteristics. Sand is loose, or it can be dense. And water table is very important. Below the water table, generally we use bearing capacity is generally, we reduce it by 50%. If the soil can become saturated, we reduce the bearing capacity by 50%. And sand, okay, no consolidation. Water settlement is rapid. Hence, no consolidation, and this settlement is initial deformation of the soil. So there's no problem, but generally sandy soil conditions, we might limit the bearing capacity to about 152 kilonewtons per meter square. Not very high, and it might be reduced to about 100 kilonewton per meter square. So we consider it as a medium soil layer, not very strong, not very weak. But it has good characteristics because it's not going to have any consolidations. Then we can have clay sand. So it's basically a sand, but it has some traces of clay, which can make it very, very weak. So if it is clay sand, we might limit it to about 100 kilometers. Then we have sandy clay. It's a very poor material. It can have consolidation settlement. It's a very high possibility. Here also you might get consolidation. So you have to be mindful about these conditions. So if you have clay sand condition, what you do is the clay sand, we can consider some local improvement for the soil. We can consider some local improvement. So we have clay sand layer. We might excavate some of the soil, loose soil, replace it with ABC 300 millimeter. So it will act like a strong pad. And on top of this, we can have whatever the foundation we like, provided it's very light loads. Provided it's all very light loads. Provided it's very light loads. Now we cannot do this with heavy loads. So that is why, these days we don't have concrete. To complete 1 meter cube of concrete, you need about 36,000 to 40,000 rupees. I'm not talking about supplying concrete, I'm talking about finishing concrete. And steel is prohibitive. The formwork is very important, very expensive. False work is also could be expensive. Now we have to think about cost-effective foundations. So what are the main differences of having the building on these 4 types of foundations? A, B, C, D. Generally no problem. B is also no problem. B is also sandy soil. When it comes to this, long-term consolidation can be a problem, and you have to guard against differential So because of that, can model the foundation with the superstructure and then see how it's going to behave, and we'll have F1, F2, F3, F4, and F5. So how can we design this? Soil is C or D type. Then we can say the total load is F1 plus F2 plus and F5 left. And we are going to divide it equally so that this will be F divided by A. So if you can apply a load like this, after modeling the foundation like this, in a T type, you can use a T section. From the whatever the software that you use, you can easily create any of these shapes, and then you can assign it as the foundation section. and you can easily do this type of foundation. And in these situations, we will not worry really about the accuracy, because you cannot say it's going to be a uniform pressure, but if you want, you can assume a uniform pressure, and then you don't need pattern loading. No need, because we are designing the foundation, so you don't have to consider pattern loading on every floor because it's unrealistic. So even if you want pattern loading, you'll consider only one floor. So because of that reason, you'll find now we have a way of actually designing the inverted T-type foundation. And to do that, we have to do a little bit of modeling, but don't do this particular model to design the superstructure. Don't do this model to design the superstructure, because the superstructure design is based on the assumption that all supports settle by the same amount, or no differential settlement between adjacent supports. So when you make that assumption, when you are analyzing the structure, you have to analyze a structure. It is wrong to analyze a structure like this and get the results, because one of the basic assumptions is not correct in this one, because there can be certain differential settlement. Then how are you going to overcome that problem? And the way that we overcome that problem is very simple, because we go for a foundation which is deep enough to ensure that the local pockets that undergo high settlement are all well looked after, because there's only one way that this can settle, and that is settling vertically down. So if that is the case, you should not select something like an inverted T-type foundation of something like 600 to 800. Instead of that, you have to consider the foundation depth as 1000 to 1200, or it can be about 1500. So always we go with deep foundations, because the settlements can be uneven, but still the chances are that we are using a very strong foundation, that all these pressures will become equalized, and after a while you'll get a pretty strong consolidated soil under the foundation, and that soil might be very useful foundation material. Okay, so basically what you have to do is always keep in mind this inverted tips is a very good foundation, because we can even support because this weak soil, generally you have to support the ground floor slab, or you can even make it structural by using a bigger, a thicker slab. Now let's see how that happens. And so if you have columns, no need to put inverted T-type foundations in both directions. You can have the inverted T-type foundation only in one direction, or it can be this way as well. But generally, we try to have these foundations only in one direction. Otherwise, it becomes pretty difficult when you want to coordinate, because there are other elements, type beams, there can be many other things. So what you do is you will bring the whole foundation, and then you can have option A, where the floor is supported on the foundation. B, where it is constructed in such a way, B can become an active member. Right. So with this condition, then you will ask, what is this B? B is, we have fairly large, we have deliberately selected fairly large spans. So we arrange the foundations like that. And sometimes we arrange a strong tie beam, or sometimes we arrange the inverted T-type foundations. So you connect with either ground beams, or sometimes you connect it with the proper inverted T-type foundation. When it is in one direction, construction is very easy. When it's when you have about these beams in both directions, construction is not that easy. Okay. So then how do you design this? We have a T-type foundation. We have these 4 beams, 4 columns. So all these are bringing in forces. Sigma F divided by the number 245 will give you a uniform pressure, force, and when you apply that, you can safely assume that the loads are pretty well distributed. The reason is the soil adjusts underneath. Because soil can adjust underneath, I generally like an ABC layer. So that these differential settlements can be sorted out. Then this ABCD is added under the foundation. So the foundation will come on top of this layer. Then what you do is you create a bending moment diagram, and we get a single diagram, no pattern loading. And you can design the also design for shear. And we do all that for this particular beam, that particular beam. And do whatever you like for the beam. So I'll check for shear. You have to check here for punchy shear, and you have to check again at that section. For shear. So generally we select shear at a distance D, and you have to do all the checks. Then you can design. Then let's assume that the soil is weak. And you like to identify what are these weak patches. And if at all soil is weak, so we can go for local improvement with ABC. And then what we do is we consider the building, whole building. This can create a computer model and then represent the soil by using springs. So you put the whole thing on springs. And when you try to do this, it crashes. So what you do is allow this way. So you have to make sure the structure moves vertically, but it doesn't move horizontally. And all these springs can be there. When you have springs, the next question that comes to your mind is spring constant. Spring constant. So to find the spring constant K, there's an equation, approximate equation that is available in the soil mechanics, geotechnical engineering or foundation engineering book by Bowles. This equation is available as factor of safety multiplied by bearing capacity multiplied by what? And you might ask how you do get this magic number of 40, and that is divided by 25, and this 25 is settlement. So basically, we are asking that the settlement should be limited to 25 millimeters. So if you have a weak soil of 110 kilonewtons per meter squared, and you have good oil of only goods, you have a weak soil of this, and the factor of safety of 2. So you have K value of 2 into 110 into 40. that is equal to 2 into 110 into 40, 8,800 kilonewtons per meter cubed. That is the answer you get. Then you have to say at which distance you are getting the. So I say let's every 1 meter we have a spring. So, and also we have selected based on our approximate calculation, we have selected an inner T-type foundation having something like 300 millimeter here and width of about 1,400 millimeters or 1,800 millimeters. If the load is very high. So our spring constant K becomes 8,800 multiplied by 1.0 multiplied by 1.4. So now you know the spring constant, you know the value that you need to apply at each location. And then what we do is we create a model. Actually, we have a model because we have already made a model. And then now we have this model where we divide it and then what we do is we apply springs like that. And once you apply springs like that, we can get a bending moment diagram that does this. So you can get it. And then you can design at these sections for it's bending upwards. So you get a lot of top reinforcement. These locations you will get a lot of bottom reinforcement. This bottom reinforcement. And here you get top reinforcement. Right. Now, the question is, will you use it directly or check the sensitivity of your answers to changes in the K value? Basically, you are trying to see whether your answer can be affected if you have weak pockets. Generally, I do not like these weak pockets. Because of that reason, I will always go for some, kind of consolidation. And also, having a proper layer of soil like ABC or semi-stabilized earth or something, whatever possible, underneath the foundation. And easiest of that would be ABC. So then what I have to do is run the same program with bearing capacity as 100 and bearing capacity as 120. Why? All our design parameters are only approximate. So it's good to do a sensitivity analysis, considering that bearing capacity can be 100 or it can be 150. And when you do this, you might end up with 2 more envelopes. And based on that, you can see how sensitive the building performs to the variations in the soil. So once you know the kind of variations that you can get in the bending moment diagram, you can do the the reinforcement calculation. And when you have a T, and when it bends this way, at support, you get a rectangular section. And in the span, you get an inverted T-type behavior. That is a flange beam. That is a flange. So, and by looking at these different answers, you can decide whether you want to go for 10% redistribution as well. So once you do the sensitivity analysis, now you know how sensitive it could be. And then you can also see what will happen when you use a foundation of 1 meter depth, 1.2 meter depth, and you can also try 1.5 meter depth. You will change the depth also and see how sensitive those answers. And once you look at this, you can see whether you have got the dimensions of the foundation properly. And you have to keep in mind that we use extra deep foundation, and then finding the reinforcement is again just a simple calculation, a routine calculation. May not be simple, but it's a routine calculation. And we come up with the steel requirement in the. So if you have weak soil conditions, you want something like a 5-story building, you don't have enough money for piling operation. Then you might consider inverted T-type foundation. And don't think your answers are absolutely correct, because they are all based on guesswork. The loading on the structure is guesswork, because we really don't know the live load. The bearing capacity is a variable, because it's based on somebody's judgment with some values. And then it's good to go for some kind of parametric study, so that as the designer, we have some idea how sensitive it could be. But if you are using a program like SAP 2000 or MIDAS, getting these answers just by changing these different parameters, variable parameters is not a major problem. Based on that, you have to use little judgment and decide the type of reinforcement. And if you look at the inverted T-type foundation, and the columns are here, these locations. And it's bending upwards, so you might need some reinforcement at the bottom. And similarly, you need, it's bending upward in between. So this is a support based on. Because it's bending upwards, now you have to think about the top reinforcement. And which is more critical? This is more critical. However, in a foundation, because we are very difficult so you have to be a little careful in dealing with this situation. Because there's a column, this area can actually shed some loads to the space. So you go for just the sufficient capacity, just sufficient here, and you will be little generous in providing and be generous. In providing reinforcement in the span section. And that way you can have a super durable foundation. And my recommendation is go for C3037 for foundation area by considering the durability and also with 25%, 15 to 20% fly ash. So for concrete, you can use about 15-20% fly ash. And because it's below the ground, control water cement ratio by controlling the total quantity of water in the concrete to about 160 kilograms per meter cube or even less. And you can easily get this by adding a super plasticizer like super by Millennium Technologies, which is manufactured in Sri Lanka. So it's very important that we understand the big picture, because when you have a beam, you have a bending moment, finding the flexural reinforcement and also checking whether it can fail in shear is not a big problem. Only this you must practice it enough so that you know what you're doing. But it doesn't mean that that you can get a good answer and a safe answer and an economical answer. For that, you have to do a little bit of sensitivity analysis. And these days with modern programs, we can do it easily. The reason is none of the parameters that you use for foundation is definitely known except the self-weight. Self-weight of the structure can be calculated with a reasonable accuracy. But other than that, the live loads are variable, finishes are variable, the soil conditions can be variable. So we have to take every precaution possible to make sure that this variability is dealt with appropriately. How you do that is by using some stronger materials, because we may not be able to wait for consolidation settlement to take place. We may need the building much before that. And if you are going for a very strong foundation, the chances are that the soil everywhere will be equally stressed or reasonably equally stressed, so that the chances for most of these variability can be reduced. But finding the bearing capacity and then finding the spring constant based on that means, again, you are subjecting yourself to a lot of judgment. So if you can do some sensitivity analysis by changing the parameters and come up with a reasonable value as your best guess, then you can find the reinforcement, check for shear, but don't make it too deep, because then it will become a deep. It might become a deep. And always keep in mind how you that these deep foundations need sidebars, because any beam of depth more than 750 millimeters will need sidebars. So whether you have actually placed the sidebars on the inner T-type foundation, in addition to the flexural reinforcement and shear reinforcement. So with that, I think I have adequately expressed the way that, what the type of soils we can find in Sri Lanka, and then, how those are originated. So basically all these low-lying areas can have deposits, and these deposits can give you a nice environment. But when you try to build on these deposits, you find that the soil is very weak, and sometimes it contains peat and so on. So many problems can be there. But one good advice is never ever build on peat unless you are designing a very lightweight structure. The reason is, when you do things on peat, it can induce a lot of unnecessary trouble as the time goes. So ideal is remove all the peat and then, create a good ground. But, if you have only thin layer of peat, when you start constructing, then, it might, when it can be removed and sorted out. So basically, if you have no peat but weak soil conditions, then the ideal solution may be going for inner T-type foundation, which is very economical, because the reinforcement here is needed only for this for the bending moments and other forces in that small section. So by going for an inverted T-type foundation, you can save a lot of headache of constructing a good foundation. With that, shall I end the lecture, Engineer Kamala?
Yeah, okay, Professor. Now it's 8:20. Yeah, it was actually very colorful and very effective lecture today. So thank you so much for your.
Yeah, thank you.
Yeah, but I will call Engineer Trimavitan for the official.
Yeah, okay, thank you.
Deliver that. Trima?
Yes, Madam. Thank you very much for the invitation. Actually, it is very useful topic today, and so we got. Actually, I was late little, but so I got many important points in your lecture, Professor. So everyone got benefited out of this lecture, I'm sure. So thank you very much, Professor. So you are every time you are sharing your knowledge with us. I mean that is very good attitude. So we can highlight. I can highlight from your side. Thank you very much for that. And so we hope you are, I mean, the sharing knowledge, your knowledge sharing with us in the future as well. And then thank you very much for all the participants who participated today, and also the IESL who are hosting this event. And so for the IT people also, I'm giving my thanks for supporting us to conduct this valuable lecture. So thank you very much for everyone, and thank you, Professor, once again, and good night. And so we'll meet once again in a day, a near future. Yeah, thank you very much, everyone. Thank you. Good night, everybody.
Good
Thank
night,
you.
everyone. Good night, Professor.